And you can see the slides right now. Awesome, awesome. People are coming early. I like that. Promising. Okay, so while we're waiting for people to join us, I'm just going to drop my bio here. So my name is Abdullah Hussein. I'm going to be your instructor today for our topic, mineral scales in oil and gas operations. I have 14 years of experience in oil and gas industry, mainly in flow assurance. And recently I authored the book Essentials of Flow Assurance Solids in Oil and Gas Operations. And recently I started this platform, CHEMDUSTRY, where we can perform or provide training and consultation. And there's also some free services like free consultation and free referral to chemical companies and other new technologies. So we will just wait here for 1 or 2 minutes for more people to join us, and then we're gonna start right away. Okay, without any further ado, let's get started. So our topic today is mineral scales in oil and gas operations. This is going to be our agenda today. We will start with a little introduction, and then we'll move to the mechanism of scale formation, and then the scale types and the factors affecting them, and then um, scale prediction, scale analysis, um, scale analysis. Just 1 second, someone texted me. Yes, the webinar is recorded. Sorry about that. So scale analysis and then scale monitoring, and then we will talk about the scale management after that. So when we talk about mineral scales, it is actually a global problem. So it's not just in oil and gas fields, it is in everything around us and in all different industries, such as the pulp and paper, geothermal, water treatment, and desalination. Even in your household items, you can see some scale in your plumbing system, in your boiler, and even on top of your shower head. So it's something we see every day. And the common thing between all of these industries and application is that they all handle water. So water is a general solvent, but in most cases it is loaded with a lot of ions and dissolved salts. And whenever these exceed their solubility limit, they just precipitate out of the solution and cause the damage. So speaking of the damage, especially in oil and gas fields, we have severe cases and damages that can happen, such as the formation damage, equipment damage, flow restrictions and blockages, and we also have this problem when the scale can cause other production chemistry issues, such as they can induce corrosion by such as the under deposit corrosion, or they can increase the kinetics of the corrosion. They also can stabilize emulsions, and they also can be a good environment for the microbial activity. On top of this, scale can be hazard materials such as the norm scale, and also can be pyrophoric scale. On top of all this, scale can be or can cause a global issue, such as the global warming. So scale can can increase the CO2 emissions, especially when they precipitate inside the heat transfer equipment. So all these damages can be represented like in terms of billions of dollars each year. The way or why these scale can be damaging is because of their features or properties. So they actually can form anywhere in the system. They are quickly forming, so they can basically, there is an example when the scale caused the production to drop from 30,000 barrels per day to 0 in just 24 hours. That was like a very severe case. Also, they also have very low solubility. They can form in a thick layers, very hard to remove. And they also, it's not just one compound. They are diverse. There's sulfates, sulfides, halides. There's all kind of different compounds. And there's also different polymorphs and phases for the same compound. So which complicates the problem and make it very elusive and needs good management from the operators. So to understand and to deal with the problem, we need to understand how scale actually formed. So we have 5 main steps. You can see them right there with the factors affecting them. We have the first one is the supersaturation. This is when the concentration of the dissolved salts and ions, they exceed their solubility limit and precipitate out of the solution. This is considered just a driving force for the precipitation. After this, we have the nucleation step. This is when the ions start pairing and form clusters until they reach a specific size. It's called the critical size, or called the critical nuclei. This is when the ionic species keep adding into it, and then it keeps growing in size. After this, the ionic species keep adding into this critical nuclei and form a physical entity or a solid particle with some crystal features. And then it keeps growing in some manners or in some ways, either like a spiral way or two-dimensional way or any other ways of the crystal growth. And then after this comes the adhesion step. This is when the solid particle that has formed will be transported and reach the metal surface, and then will stick and adhere to it to form the deposit layer. And then after time and after aging, or aging will come, this is when the flowing fluid will, with the effect of the flowing fluid and the temperature and pressure, this will cause the deposit layer to gain some mechanical strength and harden, and will be very hard to remove. As you see, these main steps have some factors that can affect them. If you have a good look at these ones, for example, for the first 3 steps, you will see the factors are basically thermodynamic. This is why we usually call these a precipitation generally. And then the last 2 steps, they are basically affected by the hydrodynamics of the system. This is why we usually call these as the deposition. So, and that should tell you the difference between precipitation and deposition. And we will need this later on in our coming slides. Someone will ask, okay, why do we need to know these theoretical stuff? This is because this is how you do your root cause investigation. That's first thing. And the second thing, this is how you actually treat mineral scales. So if you look at all the treatment methods, they all try to target one of these steps. For example, the scale inhibitor, they basically target either your nucleation step or crystal growth step. This is why we call the scale inhibitors as crystal modifiers, right? And also some of the treatment can target like the adhesion step, like the dispersion or the internal coating and liners inside the pipelines to repel the solids from precipitating or depositing into the surface. So this is how or why you have to understand these theoretical stuff. As we said earlier, scale can form in so many different types. We have the sulfate, we have the carbonate, we have the sulfide, halide. We have also silicates, phosphates, all these kinds can form, which complicates the problem because you're not just dealing with one kind. These ones have different properties and solubilities and different factors that can affect them, which makes your problem very, very complex. On top of all this, we have also the suspended solids. These are solids coming from the reservoir, such as the sand and the slit and the fines and the clay. These ones can either deposit themselves on the surface of the metal and cause the damage, or they can work as a good nucleating sites for the other types of solids, which like make the problem even worse. Of course, among these, everybody is aware that barium sulfate is probably the worst one to deal with because of its low solubility, and it's very strong and hard, and in most cases, like the chemical solutions fails to treat it. But generally, all kinds of these solids are very damaging. Also, as I mentioned earlier, it's not just the scale types. There's also polymorphs for each type. For example, for the calcium carbonate, there's these polymorphs. Same thing for the calcium sulfate, for the iron sulfide. Actually, there is more. There's more than that. For example, for the calcium carbonate, it's not just these three. These are the very common ones. There's actually like 6 ones. For the iron sulfide, there's probably 7 or 8, maybe 9. The problem with these polymorphs can have different properties. For example, for the iron sulfide, the pyrite will have very low solubility in the acid, while the other phases can dissolve in the acid. So you will need to understand which phase you have. It's not just the compound, but also the phases you have there, so you can plan the proper treatment. So now we're going to move to the next and the main and actually the very important topic, which is the factors affecting the scale formation. There is common factors everybody know about, these main factors will come into your mind whenever people talking about it or just doing their root cause investigation, such as the mixing between incompatible waters, pressure change, temperature change, pH change. These are the main factors everybody like keep tackling and keep targeting, but there's also more, such as the microbial activity, such as the geochemical interactions, the effective hydrodynamics, the production regime or the production how the production rates, the fluids rates and ratios. There's also any changes in the composition in your production fluid. We're going to look at these factors one by one because it is very important when you do your root cause investigation and risk assessment. So the first one is mixing of the incompatible waters. This is the very common and most famous factor. Mixing can happen between injection water and produced water, or between two formation waters, especially when you have commingled production. The most common scale that can form, especially when you mix injection water with produced water, is the sulfate, such as the barium sulfate, strontium sulfate, and calcium sulfate. These are very hard to remove, and they also can include radioactive material with them, forming what is called the norm. The second factor we have is the change in the temperature and pressure, and this is very, very tricky. So basically, pressure drop can cause the precipitation and deposition of the carbonates, that like the iron carbonate and calcium carbonate, also the calcium sulfates, and also the sodium chloride. Temperature drop can also cause the precipitation and deposition of a lot of scale. And the opposite of this is happening is the temperature increase can also cause the deposition of some scale. These are called the inverse solubility scale, such as the calcium carbonate. So we're dealing with a very tricky and complex. So some types are affected by the temperature and get deposited. Other ones are affected by the temperature and get dissolved whenever we increase the temperature. This is how our problem is complex. Like one factor can affect the different types differently. So you have to be really careful and understand your fluids and understand the type of skill that you're dealing with. The graph on the right is actually representing all of these. You can see almost all of the calcium sulfate, their solubility decrease with increasing the temperature. The same thing for the calcium carbonate down there. We only have like the sodium chloride solubility increase with increasing temperature, a little bit with the barium sulfate you can see at the bottom there. And then we have the pH changes. pH basically can affect the carbonate, the sulfides, the oxides, and the hydroxides in alkaline solutions. This can trigger their precipitation. Acidic solution, on the opposite, can will dissolve them. Something you need to take care of, especially when you deal with calcium carbonate, because it is very sensitive to pH changes. Actually, pH is the main factor that can cause calcium carbonate to precipitate and deposit. And there is a case when some operator try to solve a H2S in their system. So they injected a production treatment chemical. It was a triazine. And because of the high pH of that chemical, that caused the calcium carbonate to deposit. So you have to be very careful whenever you add any chemical. You need to understand your production fluids and the possibility of scale to form. And then we have another factor, which is the microbial activity. Bacteria not just can form or not just can cause microbial corrosion. They also can cause biofouling. And whenever they cause scale formation, it is called biomineralization. The biomineralization can happen in so different ways. The common one is the biocorrosion. The corrosion product in this case are called the corrosion scale. Or they can also trigger scale formation when they produce ions that can form scale, such like the carbonate or the sulfide or the sulfate, or they can accumulate the metal ions on their surface and work as a nucleating sites for the precipitation and deposition steps. We have all kinds of scale that can form because of the bacterial activity. We have the sulfides, carbonates, sulfates, almost everything. There is a case that I was involved in when iron carbonate was the main problem, was a scale problem there, and we keep looking into everything in the system. We looked at the CO2 partial pressure. It was very low. We suspected that it might cause like a sweet corrosion, and then this will be like a corrosion product. We looked into everything. We looked at like the bicarbonate and the carbonate species in the water that was very low. And eventually we found that it was bacterial activity. It was a mix between methanogenes and SRB, and we only found out this when we did the proper analysis for bacterial identification and count. We used the PCR that gave us like the exact IDs of the bacteria and the exact counts. Previously, they used the MPN technique, which gave like really low count of the bacteria. It didn't identify all types of bacteria. So you have to be really vigilant whenever you deal with the microbial activity. You have to use the proper technique because this can cause really complex and elusive damage. Another problem with the microbial activity is that it's not involved in the scale prediction software. So and this is a problem because you are not taking this in consideration. So this can be something coming from the back doors and stab your system and cause some damage. Another factor we're talking about is the geochemical interactions. In the reservoir, we have a lot of interactions such as the water reservoir rock interactions. The water can be either injection water or produced water. These interactions can dissolve some of the reservoir rock, and then they can flow through the system and then precipitate somewhere else, maybe in your well or in the top sides, whatever this can happen. We also have the thermochemical sulfate reduction. This can happen in the reservoir at very high temperatures, and this will produce sulfides, sulfates, or they can also produce carbonate as well. We also have some dolomitization process. This can be a cause for the calcium carbonate and calcium sulfate scale formation as well. Again, the problem with these geochemical interactions, this is not considered in some of the scale prediction software. So it is highly recommended whenever you do your scale prediction, if you can involve some geochemical model with your scale prediction, just to make your calculations very accurate. And then we have the hydrodynamics, and this is what we talked about earlier. There's a difference between the precipitation and the deposition. So for the precipitation, this is basically a thermodynamic process. The deposition is basically a hydrodynamic process. So for a solid particle in the flowing fluid, you might get lucky, and this solid particle not sticking to the pipe surface, I will be just transported all the way in your system until it meets like a dead end or a trap or something, and then you're good. You don't need to treat the scale. But if this particle stick to the pipe surface, then you have a problem. So there is a general saying here. They say the thermodynamics control the particles' precipitation, and the hydrodynamics, they control where these particles were deposited. So if you have like a good look at your production system and make sure your hydrodynamics are good enough to like scrub the scale or the solids somehow, this can make your system a little bit safe. Also, we have the next one is one thing about the hydrodynamics, sorry about that, is that again, like in most cases in the scale prediction software, they do not include a lot of hydrodynamics in there. And this is something that can make the scale prediction calculations not really accurate sometimes. Moving to the next factor is the liquid gas ratios. So this one basically can affect some types of scale, especially the halide scale. So whenever we're dealing with low water to gas ratio, especially in the gas systems, so there's high possibility of halide scale formation. Someone will ask, okay, halide is highly soluble. Why will it precipitate? The thing is, most of the produced waters we have in oil and gas fields is fully loaded with sodium chloride. So while the supersaturation is not there, which is the driving force, but you still have high potential. And this high potential is coming from the high concentrations of the sodium and chloride ions in your system. So whenever anything changes in the system, this high potential can be translated into driving force and then cause the precipitation. And this will happen basically when you have a system and this system have a big or significant pressure drop. What's happening is with the pressure drop, the gas can leave the solution, leave the liquid, and then whenever the gas leaves, the water can flashes off into the gas phase, and then this will evaporate the water from your fluids, and this will cause the halide to supersaturate and then deposit. We've seen these cases a lot. It can be really, really tricky as well, especially if you have very high temperature in your system as well, because whenever pressure drop, the gas evolves, then the high temperature can make the gas really dry, and this will make more water to leave the solution, flashes off into the gas phase, and this can make the case of halide scale even worse. So you have to be really careful in these cases. Also, we have the fluids composition changes. such as the chemicals we add into our production system, such as the hydrate inhibitors. These ones can trigger scale formation. We have the triazines, as we mentioned before. This can cause carbonate scale formation, or when you overdose your chemicals. We've seen a lot of cases happening all the time. Or the other way is when the chemical can change by in a physical reaction, in a biochemical reaction, or whenever by the effect of the high temperature and pressure. So, for example, we have the THPS. This can be a source of sulfate. The bisulfite can be a source of sulfate. These can form sulfate scale after that. And also, we have some corrosion inhibitors can decompose in the system, and then they can form H2S, and then will cause corrosion and iron sulfide scale formation. So you have to be really careful when you deal with this, like making sure you're adding the proper chemical. It's compatible with the fluids. It's compatible with the parameters and with the metal structures you have there. Then we're going to move to the next step, is the scale prediction. This is the main or the main step in our scale risk assessment and root cause investigation as well. So scale prediction we can do this by so many ways, either using the software packages. These are the commercial ones. And also we have the saturation indices and the scaling indices. In addition to this, there is the AI, or the artificial intelligence. This is like really developing technology. I'm pretty sure it's going to take over the whole thing in just a few years. So speaking of the scale prediction using the commercial packages, so we have some examples such as the ScaleSoft Bitzer, we have the Multiscale, French Creek, Scale 2000, and of course the ScaleChem. These softwares will look like a black box to most of us, but actually the background behind them is very simple and basic chemistry class. So if you have a sparingly soluble salt, you can represent its equilibrium according to the KSP equal to its ionic product, and then you will have three basic cases. Either the KSP is higher than the ionic product, and then there will be no precipitation, or equal to the ionic product, then we have equilibrium state, or when it's less than the ionic product, and then you will have a precipitation. So this is, as I said, this is a very basic chemistry class, but we cannot use this in our oil and gas scale prediction for so many reasons. The first one is, first of all, we have to represent the equilibrium using the activity coefficient. And why is that? It's because our produced water have very high ionic strength. It is fully loaded with ions, so you cannot just represent it using just the concentration. So you have to include the activity coefficient. That's the first one. The second one, these ionic activity coefficient and the KSP values, the ones that we have right now, theoretically, are just made at like very low temperatures and pressures and ionic strength. So we have to model these and calculate their values at very high temperature and pressure and ionic strength. So that's the first problem. The second problem is we do not deal with just water phase. In oil and gas operations, we deal with oil, gas, and water. And between these, there is compounds that like floating around between all these phases too. So we have to understand the phase equilibrium between all of these phases, so that we can determine what components in what phase. Especially when we deal with the H2S and the CO2, these ones are very critical to determine the pH of our water, and also and also they are crucial for the carbonate and the sulfide scale calculations. So for these reasons, we have to do some calculations It is called the flash calculations. This is when we calculate the phase equilibrium between all of these phases. So the main organization for the scale prediction software, so we will have an inputs. These inputs will be the water chemistry, the pressure and temperature of your system, the produced fluids rates and volumes, and highly recommended is the hydrocarbon phase composition as well. I know some people do not do this. It's because the scale prediction software you have right now, they have like a default hydrocarbon phase composition. They use it for all the calculations. But if your oil phase or your hydrocarbon phase is very different from this default hydrocarbon phase in the scale prediction, the calculations will be very different. Let's say your oil has an API of 12. Let's consider this, and that one in the scale prediction is like by default, let's say 25 or 30. So this big difference between the properties of oil can give you different calculations. So this is the inputs, and then we have the calculations. We do the flash calculations, and we do the activity coefficient and the KSP and other properties for the phases, like some physical properties like the viscosity, the density, and all these stuff. And then we have the output, which is the scale masses, the scaling indices, the amount of inhibitor that we need to inhibit the scale. And also they usually calculate the pH of the water, and also they do some calculations for the water phase properties. So the scale prediction software are not just used for the scale prediction. You can use them for other applications as well, especially when you look into the features inside each software. We also have in the scale prediction, we have the saturation index and the scaling index, such as the LSI, and these other ones you can see there. These ones are of limited use, especially in the oil industry, and also some of these are actually integrated inside some of the scale prediction software. Okay, now we're going to move to a very critical topic, which is the scale monitoring. So you can monitor the scale, and this step, the scale monitoring, this can be done either before treatment or after treatment. So you can do it before the treatment, just to make sure your system is safe and to detect the scale at its earliest stage, or you can do it after the treatment as a method of assessing your treatment. So the basic things we can do for the monitoring is we have to monitor the production parameters, like any pressure drop, any temperature drop, any productivity drop. All of these can be indicators of scale formation. The temperature, this is very simple. You can just get a temperature gun and point it at one of the pipelines. If you see any drop in the temperature, this is indicator that there is insulating scale layer inside that causes the temperature to drop. There's also the chemical analysis for the produced water. Any drop in the ions concentration is indicative of your scale formation. There's also some sensors that you can use. There's a common one that has been developed recently using tomography technique. It's by a company called Roxol. These ones are very effective, and they can detect not just the scale but all types of solids as well. There is ultrasonic ones. There is electrical, magnetic, or electromagnetic detectors. But the one using the tomography is very effective. I would recommend that one. We also have the last one is the total suspended solids, and this is a very effective method of doing scale monitoring. So you basically, as we mentioned before, so we have precipitation and deposition. So what's happening here? We're going to collect the solids from the flowing fluids and assess the problem. So this is all about that. So the TSS is basically a water quality test we usually do for the injection water, but we can do this for the produced water to monitor our scale. You can do this in a very simple way or in a very advanced way. The simple way, you can just collect a water sample, filter through membrane filter, and then you will the solids collected on the filter. You can determine the composition either using like ICP or something, or even the wet chemistry. If you collect like significant amount of solids, and then you can make relationship between the solids collected and the produced flow, the produced water over time, over a specific period of time. And then you can assess the problem. This is a very simple way to do it. Or there is also advanced way. It's called TSSESEM, or also called the bulk scale analysis. There's a company that can provide this service. It's called Scale Protection. So what they do is they collect the fluid, a sample of the fluid, and they filter the water, and they take the water. And they take the filter paper and they assess the problem by the surface coverage, and then they determine the solids composition using the SEM, and then they will tell you if the solids there are actually actively forming or transporting or modified. And this will tell you, especially if you're doing a treatment like injecting a scale inhibitor, if the solids are actively forming, that means your treatment is not working. But if they are modified, that means the scale inhibitor is actually working good, and so on. And then they can make like a risk matrix between the surface coverage of the filter paper and the produced volumes, and then you can assess the problem. This one is very effective and very efficient, especially after the treatments. And the company there, they have a lot of case studies of this method of monitoring scale. So now we're going to move to the scale analysis. First thing, we're going to collect a sample either after pigging or gauging operations, and then we're going to test for radioactivity just to be safe. And then we're going to do some inspection for the sample and see the physical features of it, the thickness, the color, the texture, or any contaminants in there, just to make sure our sample is what we're looking for. And then we're going to prepare the sample. We're going to wash the organics, and then going to either dissolve it in a proper solvent, or we can just skip this part and use the solid sample and analyze it as is. And then we can determine its composition at the end. Scale analysis is actually very critical. It's because your main treatment is actually relying on that, how accurate your analysis is. So you have to determine the main composition, and you have to determine the phases as well. As we mentioned earlier, different phases of the same compound can have different solubilities and properties. So you have to make sure you determine the composition and also the phases. This will help you in the root cause investigation and in your treatment design. Also, another note is that if you can determine the composition of each layer separately. Let's say you have your scale layer is thick and have like different layers. If you can determine the composition of each one separately, this will be great. The reason behind this is again, this is useful for the root cause investigation, and also useful if you're trying to do a chemical scale removal. Let's say different layers have different composition. So, and also let's say the first layer is acid soluble, and then the next one is acid insoluble. So you can do like multi-step cleaning. So first you will wash the first layer with the acid, and then you will wash the next one with another dissolver, let's say the EDTA, for example, and so on. So, or you can, if you know the exact composition and the phases, you can target specific compounds in the scale layer, and afterwards the rest of the scale will just disintegrate. Its mechanical strength will disintegrate if you just target, let's say, a cementing material inside. inside the scale layer. So if scale analysis is done properly, this will be like something really helpful for the treatment. Now we're going to move to the scale mitigation. So we can either prevent scale from formation or removing the already formed scale. The scale prevention can be done either by chemical methods, non-chemical methods, or operational methods. So for the operational methods, you can just take care of little things in your system that will help you to prevent scale from forming. For example, if you can choose the water sources at the beginning, if you're trying to do water injection. The second thing, if you can avoid mixing of incompatible water. If you can properly design your system so that if you have incompatible waters, you can avoid this. For example, if you can like add more rerouting and bypasses in your system. So if you feel there's these two fluids are incompatible, you can reroute one of them or bypass this one and so on. And also if you can do injection water, so like the injection water systems. So if you can pre-treatment these ones, removing the dissolved the acid gases, removing or using the ion exchange, and recently if you can remove the scaling ions. And this is a very common technique people using right now. It's called the sulfate removal process. And this one they use nanofilters to remove the sulfate from the system. And this has a lot of benefits. It's going to prevent sulfate scale from formation, and it's also going to reduce the SRB bacterial activity. Basically, they use these ones, especially when when your production system is very big and the chemical treatment is very expensive or not really effective. This is, and there's a lot of cases of success for these SRP processes. Also, you can prevent scale by taking care of the suspended solids in the sand and fines production. The next treatment is the chemical prevention. And this one we use what is called the scale inhibitors. So we have thermodynamic ones like the acids and the polyaminocarboxylate. These ones are added in a stoichiometric rates. And then we have the threshold inhibitors. These ones are added in a very small concentrations and they do their magic. For the threshold ones, we have different brands and different compounds. We have phosphates, phosphate esters, we have phosphonates, and all different polymeric materials. For the threshold inhibitors, they work, or their mechanism of work, they can work either by crystal modification, or they sequester and prevent the nucleation step. They interfere with the nucleation step, or they work by dispersion. We also have some new chemicals. We call them the green inhibitors. So these can be like natural extract, or we have the nanomaterial, we have ionic liquids. These ones have been used in the fields and showed really promising results, especially the nanomaterial. They were found they are really effective and they can extend the scale inhibitor squeeze job duration. We also have the dispersant. We usually use the dispersant with the iron sulfide scale. And then we also have another option, which is the water shut-off chemicals. So what's happening there is instead of like going after the scale and try to treat them and stuff like that, we can just stop the problem from the origin, adding some chemicals to your reservoir, and then this is going to stop the water producing channels or reroute them. So these will not cause the damage. Before you treat your system with the scale inhibitor, so you will have to do some tests. First, you have to look for their efficiency. You do static precipitation test, the flow loop test. There's also the kinetic test and the adsorption test. The main reason for doing this is we're looking for the minimum inhibitory concentration. You also have to make sure that these chemicals are compatible with the produced fluids and the production chemicals. You also have to make sure they are compatible with the metallic structures you have there. And also you have to make sure they are thermally stable. The application of the scale inhibitors, we can inject them, continuously inject them in the system, or we can batch inject them either by either with the fracking fluids or by doing the scale inhibitor squeeze. This is the most common one. There's also the solid inhibitors. These are encapsulated solids we can add just to the system in the rat hole, and then they will slowly release and protect your system. Or we can add them with the fracking propellant. And lastly, we have some other applications like the foam inhibitors, the gel inhibitors. These are all different applications, but the most common one is the scale inhibitor squeeze. This is when we pump the chemical down into that reservoir and let it settle there for a while, and then we shut down the system to make the inhibitor retain on the reservoir rocks, and then we flow back, and with the flow back, all the scale inhibitor will slowly release, and they protect the system from the point of injection, or from the first point until whatever after this. So from the reservoir and to the well and then to the top sides. So what you do is you place your scale inhibitor, you do a pre-flush to just condition your reservoir formation, and then you inject your main treatment chemical, and then after this you overflush with some chemicals to make sure they are in the right location. After a while you shut down your system, you let them retain either by precipitation or by adsorption, and then you restart your system and let the scale inhibitor do the magic after that. After you do your treatment, you have to assess. Basically, you can do this by physically looking into your system using the either the pigging if it's in the pipeline, or the gauging in the wells. And you also can do the scale inhibitor measurement. This is the most common one. And this one, you have to make sure your inhibitor concentration is not below the minimum inhibitory concentration. And then after this, you also can use some sensors. And again, you can use the total suspended solid method or the bulk scale analysis. Again, this is a very effective and very efficient very efficient one. Then we have the non-chemical scale prevention. So in this case, we can use the magnetic methods. We can use ultrasonic, but the most efficient one people are using these days is the electromagnetic one, and this one is provided by a company called Clearwell Technology. This one is using the electromagnetic, and they have so their device produces radio frequency beams, and these ones try to prevent the scale in your system. And then we have the mineral scale removal. So the removal can be done either by chemicals or by non-chemical methods. So either way, if you're using a chemical one or a non-chemical one, so you have to know a little bit about your scale that you have in your system. So you have to know the scale type, just in case you're using the chemical dissolution method, if they are acid soluble or acid insoluble or water soluble, which one is that? The second one, you have to know the physical features of it, the thickness, the hardness, the thickness, the hardness of your sample. You also have to know where your scale formed. Is it downhole, or is it in the top sides? Whatever your scale is, will there be a good access to your scale to the obstruction there or not? If I'm using a mechanical method, will I have a good access to the location of the scale to treat it or not? And after this, we need to have a proper time for the treatment, and also if there is a possibility to use a combination of methods. So just in case you used the chemical the chemical scale, the chemical treatment method to remove your scale. So there's no universal dissolver for all types of scale, unfortunately. So we have to treat every type of scale kind of separately. So for sulfate scale, we basically can use the chelating agents such as the EDTA and DTPA or the crown ethers. We can use like some converters, and there's also some new technologies have been used recently by some companies like Enospec. They used they developed some dissolver for the sulfate scale. But either way, if you're using the chelating agent, you will need a lot of time, you'll need heat, you will need high pH, and you will need also patience. You have to be really patient with that. You might need to do a couple rounds to remove all the scale from there. For the carbonate scale, you can use acids or you can also use the chelating agent. The problem with the acid, they can be corrosive to your system, so you have to be careful with that one. With the sulfide, with the iron sulfide scale, you can use either acid or you can use chelating agents, you can use biocides or oxidizers, or you can use other polymeric materials. So for the acid, it has a lot of problems. They can be corrosive to your system and they will not dissolve the pyrite scale. That's a big problem. For the chelating agents, they will dissolve it, but they will require a lot of time, and sometimes they're not really efficient. You can use also the biocides like the THPS, potassium permanganate, and stuff like that. But these ones can be a little corrosive to your system, but they have been used and they were really efficient. There's some recently developed products like the oxidizers, and these there's not a lot of case studies for this one, but people were talking about it. And there's also polymeric materials. I don't know the exact composition of it, but people are actually like mentioned their use. For the zinc and lead sulfide, you can use either the acid or the chelating agents or the biocides or also the oxidizers, same thing like the iron sulfides. But there's some little problems here. With the iron sulfide, again, the acid will produce H2S, dangerous material, and in some cases it will not dissolve the zinc sulfide. So that's another problem. A third problem is you might dissolve the lead sulfide, but you have a possibility of forming lead chloride, and this is a big trouble to your system. So you have to be careful whenever you use acid with the lead and zinc and lead sulfide. We also have with the chelating agents, these are really, really slow in dissolving the zinc and lead sulfides. The biocides are really efficient, but they can be corrosive. The oxidizers and the polymeric materials, these are not really, there's not a lot of case studies for these ones. Finally, we have the halite scale that you can dissolve this using just the fresh water. And then we have the mechanical methods of removing scales. So we can use either pigging, wireline, and slickline methods, coil tubing, and any other developed methods. Again, this will depend on where your scale is forming. Is there a good access for these tools to get in or not? Is the obstruction really heavy, or it can be like removed easily? So the holistic scale management strategy will be, first thing, we will collect samples, water and hydrocarbons, and then we'll do risk assessment by doing scale prediction, and then include some case studies. Again, with the scale prediction, you have to be really careful. You have, if you can, involve geochemical model and reservoir simulation, especially if you're trying to do a scale prediction in a production well or in a reservoir. That will be great. This will make your results really solid. And then after this, we will use the monitoring. We will plan our treatment, either chemical or non-chemical. After we apply the treatment, we will monitor for any advances, for any we will assess the efficiency of our treatment method. If it's great, then that's good. We will keep monitoring. If it's not that great, we will either reassess the treatment methods or we will reassess our management plan from the beginning. So that's all about it. And now, if anyone has any questions, we are good to go. So I have a question regarding CHMU, like deposit, which is a mix of emulsions and FES found in water injection wells. What would be the best mitigation in terms of chemicals? Okay, we actually have we have a kit, and it wasn't really schmo, but it was iron sulfide scale in one of the injection wells that reduced the injectivity of the well. So what happened is we increased the biocide. In our case, I'm talking about this case. I was involved in injection the biocide improved the injectivity afterwards, and we've seen like less iron sulfide scale there. We use THPS, so it's a biocide, and it also can work as a good dissolver for iron sulfide scale. So you can try that one if you want. But you have to understand what is the cause of the problem. So in an injection well, and you have iron sulfide, I'm assuming there's a bacterial activity. If you're using one of the techniques that is not really accurate in detecting your bacteria, then you can try to get like a good technique like the PCR or any of these techniques. This will help you to get a realistic IDs and counts for your bacteria, and then you can start from there. Is there any chemical that dissolve the barium sulfate? Okay. There is dissolvers, but again, as I said, these dissolvers will depend on they will need high temperature, basically above 70 degrees C. They will need high pH between 10 to 12. They will need if you can provide agitation, this will be great. And they will need a lot of time. We have done a case, and it took 2 to 3 days to dissolve barium sulfate and strontium sulfate. It worked, but it took again a lot of time, 3 to 4 days. I don't know how do you manage your production system there. And also if you can do this in multiple rounds, you can do one round and see the effect, second round, third round, and stuff like this. So that is one thing. Second thing, you can promote or enhance the efficiency of the chelating agents. So what we did is we use phosphonate as a catalyst. Some people used peracetic acid. There's a paper published using peracetic acid. Some people use thiosulfate as a catalyst. Some people use potassium oxalate, I think, as a catalyst to improve the efficiency of the chelating agent. You can try this. The most common chelating agent, by the way, is the DTPA. That's the one that has the highest efficiency in removing barium sulfate. So that's for the cheap options. For the little bit expensive options, there's a company called Enospec. They said they have like a chemical that has like working like a magic. There's also FQ chemicals. They said they have a chemical that works like a magic as well. Let's go back to the cheap ones that we mentioned, the chelating agents. You can also induce the efficiency by using like a mechanical method with the chemical that is injected as well. I hope this answered your question. So sometime face norms curative, what usually the best strategy to mitigate it? Again, the norm scale, most of the time the norm scale will be forming with it'll be forming with barium sulfate. Again, this will be the same answer I gave to Hassan earlier. Are there any routine cleaning procedure in process? No, we cannot do this. Not in a big production system like subsea and deep water systems and offshore facilities. We cannot do that. What did we supposed to do if the barium sulfate present in the well? Yeah, well, barium, if you have a threat with barium sulfate, you have to work very quickly. You have to plan your mitigation with your chemical provider. Scale and squeeze inhibition, as you mentioned, it's in a well, so a scale squeeze will be your best option. And you have to get it, and you have to do frequent monitoring of your produced water using the TSS method that we mentioned earlier. You have to watch your productivity, your pressure and temperature. Again, barium sulfate is a huge threat that can clog your well pretty fast. When you have when you have layered scale combining mineral and organic, what the best solution to dissolve scale? So that's a good question. So basically, you can wash off the organic material first, and then you can try your dissolver for the inorganic ones, depending on their composition. And again, as I said, with the scale dissolution or removal, you have to be really patient. You have to maybe you will have to do a couple rounds, 3 rounds, maybe four, whatever you want. You can try the cheap solutions, the cheap dissolvers, as I said, like the chelating agents and stuff like that. Using desulfation unit all the time, there is issue about efficiency of removal cell, and hence you cannot protect the whole system. Of course, yeah. Well, it depends on how you run your desulfation unit. Are you doing like good maintenance and doing like washes and all that stuff or not? But there is a lot of case studies. They mentioned that they are really efficient. After using HCl and G. Okay, you cannot know for sure if it's corrosive to your system or not until you do some monitoring to your system. So before you apply your treatment, you have to do some lab work, usually using like a coupon or something, and see your corrosion rate. So that's the first thing you will do. And of course, if using HCl, you will add some corrosion inhibitor there just to make sure your system is not going to collapse, right? After you do this, it is highly recommended if you can check on your well, especially if it's in a well in a downhole, as you said. So check on this one and make sure that your well is actually in a good condition. If it's really old in service, let's say 15, 20 years, if the material is not really corrosion resistant, then you might need to do a checkup on your well down there before you inject the system. That's one thing. Or the second thing, your wash, instead of using it for, let's say, since you're adding HCl, like you can just reduce the contact time, and instead of like half hour, it will be like 5 minutes. Instead of like 10 minutes, it'll be like just a quick flush, and you can repeat this. Or you can just do a flush of your dissolver and then water flush afterwards, and then do another flush of your dissolver. Again, the process of removing scale, a lot of operators, they think it is like magic. Yes, it is like magic, but if you do it properly. So you have to understand your system, your scale, how thick they are, how old they are, and how solid your system is. In prediction, should we use total iron content or dissolved iron, since too much if ES in the system? This will affect the inhibitor efficiency. I would recommend the total iron content, since, as you said, the dissolved one might not represent the system, but that also still depends on where are you trying to do scale prediction for. So are you trying to do scale prediction in a well or in a pipeline? So if it's in a pipeline, yes, there's a high potential that some of the iron will just precipitate. So the total iron will be your best guess. But if you're doing in a downhole, it is recommended to get the sample from the downhole. So a downhole sample will be really necessary. In scale testing, any non-carbonate acid-soluble minerals, iron hydroxide, will get oxidized in loss of ignition. Will this be considered as acid-soluble? Well, as per your question, yeah, it might be, but in the same time, you might need to change your if that's the case, you might need to change your night to change the technique that you're using for testing your scale there. So I would recommend this. I know it might be hard. It might be the only technique you have in lab, but you might need to change that one if it's like giving you wrong results and not really properly interpreted. Thanks so much. It's quite difficult to understand scale mechanism. Yeah, you are most welcome. Yes, I will post the recording on YouTube, and I will send you. I think I have your emails since you all registered, and I will send you an email with the slides as well. All right. Any other questions? Injection point order for the same pipeline for corrosion. For corrosion and scale. So yeah, that's a very good question. Talking about how to which you're talking about which one will be before the other one when we talk about the chemical injection, right? So yeah, what's happening here is in your system you will need to add the scale inhibitor before the corrosion inhibitor. So whenever and you have to make sure that there's enough distance between them. Scale inhibitor will react with the chemical with the scale forming species, protect your system, and then will be consumed before it goes to the corrosion inhibitor, which is going to make like a film on the pipe surface to protect it. But if you did the reverse, if you added the corrosion inhibitor first, then it's not going to solve the scale problem, and then it'll make some film on the pipe surface, but then it's going to meet the scale inhibitor afterwards, and then it's going to diminish its efficiency. So in this case, will be scale inhibitor first, and then corrosion inhibitor after that, with a proper distance in between. Okay, thanks everybody. I think that's it. That's it for today. I'll be grateful if you guys can leave your comments about this presentation on LinkedIn or even here in the chat. And we'll see you soon. Thanks everybody.